Hi class, we're going to look at solution concentration today. This is a really important concept in chemistry. We're making solutions, we have a solute and a solvent, but how concentrated or dilute is the solution? And how do we quantify this? Well, of course, we use a ratio for concentration because it's a comparison of solute and solution amounts. The solvent is part of the solution, but it doesn't get quantified. So the ratio here in solution concentration is defined as quantity of solute divided by quantity of solution. There are three main types of concentration which we're going to look at. Visually we can see dilute and concentrated shown here, but typically solutions are not visible in the particle size, of course. So the one phase homogeneous mixture definition of a solution still applies. We can't see the particles. We can't tell the difference between one which contains much solute and one which contains little. So we need to use a quantitative ratio. And when we get into the types of concentration, I would say maybe the most common type of concentration that you would encounter if you start to look at household cleaners or solutions found in the home, percent concentration is commonly used. There are three sort of subtypes of percent concentration. They all tie back to 100 units of a given volume or mass, depending on, if you see in your handout, whether the percentage concentration is per volume or per weight. It would be over 100 milliliters or over 100 grams. Of course, percent, it's always out of 100. The volume to volume is just a simple ratio of two volumes. The weight to weight is a ratio of two masses, and the weight to volume is a ratio of a mass to a volume. And in percent concentration, proportional reasoning, because when we have a value out of 100, it's more natural to just use the relationship between the concentration and either the mass and the volume without necessarily referring to specific variables. So I'll give you some examples here in your worksheet. You're going to be solving some questions, and you can compare those to the answers that will be posted on the website. Some practice questions have also been included, which you'll find in your handout package, and the answers to those would be in your textbook. So we're in section 6.3, so you'll find the solutions to those on likely pages 284, mostly, in the margins, so you can check them. I'll just set up a couple here just to show you how percent concentration works. In this case, it's a percentage by volume. So the two quantities are volume. So we're going to look at percentage volume to volume for gasohol, which is a mixture of ethanol and regular gasoline. So 55 liters would be the volume of the solution, and 4.1 liters would be the volume of the solute, which in this case is not a solid, it's a liquid. So this is a liquid-liquid solution. And then when we convert this, the only other thing we have to remember is that percentage from a decimal requires us to multiply by 100. So when we get our final answer, report that to two significant digits, and your unit here can either be percent, and when you check your answers here, you'll find that this one is 7.5%. So 7.5% is the answer when we divide 4.1 by 55 and multiply by 100. However, 7.5 liters per 100 liters would be one way of reporting this, alternatively. Or if you go with the milliliters per 100 milliliters, this matches the units that are shown here on your summary sheet. I would suggest that liters per 100 liters is a little bit more fitting given the amount of fuel that usually you pump into a gasoline tank. Okay, number 4 is a solid-solid solution. So this is an alloy, a mixture of copper and zinc to make brass. So if we have a small amount of zinc and a larger amount of copper, we could sort of say that copper is the solvent. And in this case, the weight percent or percent weight to weight. In this case, it's going to be a ratio of two masses. It's going to be the mass of our solute, which would be the zinc, divided by the mass of the solvent, which will be the brass. So we have a 35.0 gram pendant, so that would be our solvent or alloy mass. We have 1.7 grams of that is zinc. Multiply that by 100, and then when we get our answer there, it's 4.8%. So 4.8 has been converted into percent. We could either call that grams per 100 grams or 4.8% by weight. So percentage concentration usually is a real simple ratio of two different values, which may have the same unit or different units. When we look at applying percent concentration in your worksheet, you'll have some questions which will have you using percentage concentration in here. Numbers 1 and 2. You're working with grams and milliliters. In both cases, you're looking for a mass in number 1 and 2. So just to sort of set this one up, to give you an example of how you don't really need a formula, the 4.5 grams per 100 is your concentration. So that's your C value, which is really 0.045 grams per milliliter if you divide 4.5 grams by 100 milliliters. And the 250, of course, is the volume. So this here is matching the units for the concentration. So in a sense, according to the formula, it's mass divided by volume. So therefore mass would be concentration by volume. But a lot of students would look at that and say, well, if I have 0.045 grams for every 1 milliliter, I'll just use proportional reasoning and I'll say I'd have to multiply by 250 milliliters. My units of volume would cancel and I'd be left with units of mass. And the final answer can be reported to two significant digits, which in this case, if you check your answer on the worksheet for number 1, is approximately 11 grams. So again, there, you could think of it as the use of the formula M equals CV, or you could just use a simple ratio, which is your concentration units, grams per milliliter, and multiply by your milliliter, and you'll end up with gram mass. So whether you use a ratio, proportional reasoning, or whether you use a formula, it's really easy to solve percent concentration questions. Number 2 is pretty much identical to number 1, except the percentage is given at 10%. So that would be 10 grams per 100 milliliters, which as a decimal, 10% is 0.1. So again, you could be multiplying 0.1 by 750. So when you go through these questions here, you'll find some will be easy to solve with the formula and some don't require a formula. Going back to concentration again here, let's look at the other types. So molar concentration we may have encountered before in this course. We're very familiar with the mole. And so molar concentration is simply defined as the number of molar units in a liter of solution. So concentration equals N over V is going to be the summary formula for molar type. And in this case, you may have different units. You may see millimoles per liter, depending on how dilute the solution is. And when we go at trying a couple questions involving molar concentration, quite often the chemical formula of the substance is included, which is important because in number 19, we're being asked to solve for a mass. So let's look at 17 first. Here we have the number of molar units given for sodium sulfate, which is 0.14 moles. The solution will have a concentration required of 2.6 moles for every 1 liter. And the volume here is being required. So what volume would you dispense? Well, concentration for molar type is like molar density. It's number of molar units divided by the volume. So therefore, from that, volume would be the number of molar units divided by the concentration. So we can see how many times will 2.6 divide into 0.14? Well, not even once. So this number of liters that we're going to need here is going to be much less than 1. And in this case, your answer for this practice question number 17, you'll find on page 288, ends up being 0.054 liters, approximately to 2 significant digits. Now I would just say here, because it's a very small liter amount, I might suggest that you convert that into milliliters. And to convert, not a lot of space to show this, but to convert 0.054 liters, you'd multiply by a ratio, knowing that there is 1,000 milliliters for every 1 liter. We would just be multiplying that value by 1,000 and we end up with an answer of 54 milliliters. So if you're wondering why the answer there is in milliliters, just be more appropriate unit to use. Okay, number 19 is very similar, except 19 requires you to eventually calculate a mass. So when the mass is unknown, there's going to be a two-step solution to this problem. So looking at the units would identify the type of concentration. So mole per liter is the concentration type. And here the value is 3 liters for the volume. And we're looking at trying to solve for the mass. Well, the mass can't be solved for until we know the number of moles. So here I would set this up as moles equals concentration times volume from our molar concentration formula. So we're just going to be taking our 0.125 mole per liter, multiplying that by 3.00 liters, and then from there that would be 0.375 moles. That's how many moles of sodium hydroxide are required. Sodium hydroxide comes in units, where the molar mass of sodium hydroxide is about 22.99 plus 16.00 plus 1.01, which would be about 40.00 grams for every 1 mole. So that's the molar mass. And to calculate mass, we just take number of moles multiplied by molar mass. So we need about 1/3 of a mole, so we're going to need approximately 1/3 of 40 grams. It's a little bit more than 1/3, but just to kind of help you see how that reasons out, it's going to be 40.00 grams for every 1 mole. And again, here this ratio shows that the units will cancel out, and our final answer there for number 19 is 15.0 grams. Actually, that would be exact. Okay, so molar concentration can be well connected to mass using our familiar formula that we've been looking at a lot in this course. Molar concentration is going to need to be used in number 5 and 6 as well as 7. So when you're working on these in class, those 3 will use that type of concentration. So the final type to look at here would be 3 as well, I'm seeing, would be number 4, which includes an unfamiliar unit to it, which is part per million. And maybe you've heard of this before when you hear in the media about say chemical spill, or hear about a chemical contaminant, or maybe a water treatment center detects the presence of E. coli or nitrate or some toxic heavy metal in water, and they quite often report it as part per trillion, maybe part per billion. So very, very low concentrations will be the 3rd type of concentration, which are all on the very dilute end of the spectrum. One of the real key things for you to understand is that these are aqueous solutions, and because there's such a small amount of solute, the density of the solution is approximately equal to the density of water. Okay, so what that means is a milliliter of the solution will have a mass of approximately 1 gram. A liter of solution, 1,000 times as much, would have a mass very close to 1 kilogram. And I hope to be able to confirm or at least demonstrate that to you in the class. You can see that when you make a solution with a solute, even if you have a significant amount of solute, actually the density usually doesn't drift very much away from the density of pure water. So this is something to remember, that when our solution is made up, if we know the volume of it, we quite often know the mass of it in different unit but equivalent numerical value. So here, the sort of subtypes for very low concentration, they are all weight-to-weight concentrations. And so it's sort of a special case of percent by weight, but in this case, this would be weight to weight, looking at a part for 1,000, a part per million, a part per billion, and we could go beyond that if it was extremely low concentration, part per trillion. When we look at the part per thousand, let's try to reason this one out here before we look at how to calculate some values related to ultra low or very low concentration. 1 kilogram of solution is approximately going to be corresponding to 1 liter. And here, of course, so a gram of solute and a liter of solution would have a concentration of 1 part per thousand. Okay, so we can almost think of this as a gram out of, well, what's a 1 liter? It's approximately 1 kilogram. That would be 1,000 grams. So you can see clearly 1 out of 1,000 is 1 part per thousand T. If we look at a part per million, okay, well, here a part per million, let's stick with the liter as our sort of base unit for volume. So part per million, we want to start with, in this case, be 1,000th of the amount of solute. So it's not in the gram range, it's in the milligram range. So we have sort of 1 milligram, and again, keeping in mind that a liter is about a kilogram of mass for this solution, which is 1,000 grams. Well, how many milligrams is 1,000 grams? It's a 1,000 thousandths. Okay, so 1,000 grams is 1 million milligrams, and obviously 1 out of a million is 1 part per million, m. So we can make real easy comparisons here with making the units common, and then it's very easy to see why it's 1 out of 1,000, a part per thousand, 1 out of a million, part per million. There are other related units to these that don't necessarily involve the liter or the gram. We can go to, for part per thousand, we could go a gram per kilogram. That's kind of almost implied here, that gram per liter is the same thing as saying a gram per kilogram. So if you had a gram of solute and a kilogram of solution, that'd be a part per thousand. When you go to the part per million, we've seen the milligram per liter as our sort of base unit, I guess, for part per million. We could also say that's equivalent to a milligram per kilogram. Okay. And we could also back off and say, well, if we wanted to go to a smaller amount of mass, like instead of a kilogram, use a gram, then we'd have to scale back by a factor of 1,000 on our mass. So now we're not talking about a milligram of solute, we're talking about something which is 1,000 times smaller than a milligram, and that would be called a microgram. Okay, so the sort of Greek letter there, which is mu, is representing the prefix micro for unit. So we've seen milli, we've seen kilo, we've seen mega, maybe in some cases for very large amounts, and mega means million, micro means millionth. So a millionth of a gram in 1 gram would also be a part per million. Okay, now if we go to part per billion, this one here is our last sort of very low concentration here. In this case, now that we've introduced the micro, micro means millionth. If we want to have a part per billion, we really want to end up with 1 mass unit in a billion solution units. So we could go with a starting point where we use, so it could be like 1 gram and a billion grams would be a part per billion, but might be easier to start with, okay, a liter again. And if we have a liter of solution, that would again be 1,000 grams. We would need a millionth of a gram to get our part per billion. And a millionth of a gram is, you know, we could write it as 1 millionth of a gram, but a millionth of a gram is a microgram. So microgram per liter would be our part per billion. Of course, we could also call it a microgram per kilogram because of the equivalence between those two for aqueous solutions. And we could also, if we wanted to go down to the gram scale instead of a kilogram, let's get 1,000 times smaller from a kilogram to a gram. We'd have to get 1,000 times smaller in the amount of solute. So remember, some of this can be a little tricky when we get into the part per million, but going back to the basic definition of concentration, here we have concentration being amount of solute for an amount of solution. So if the denominator of this ratio is always the amount of solution, then a gram of solution, for it to be a part per billion, it's an extremely small amount of solute. It's a fairly small amount of solution, a gram, and a gram would only be a milliliter in an aqueous solution. So a thousandth of a microgram is called a nanogram. So in the very small end of the scale, we have unity, which is 1, and then we have on the right side we have thousands, which is the prefix kilo, and then we have 10 to the power of 6, just to abbreviate here, this is 10 cubed. We have mega, and then 10 to the power of 9, which is billion, and then we have 10 to the power of 12. And for, I think some of these very large values, I believe trillion is, I think billion is tera, and I'm not sure about the trillion. I'd have to verify that, but we're dealing with the opposite side of the scale. So when we have a thousandth, which is 1/1000th or 10 to the negative 3, this of course is milli. And then when we have a millionth, we have 10 to the negative 6, this is the micro. And then when we have a billionth, this is the nano, okay? I think 10 to the negative 12, a trillionth is femto. Okay, so those prefixes, if you're not used to seeing them before, for very low concentration, the nano and the micro become more useful with our units. And all this does is it just allows us to have a little bit of flexibility with the definition of a part per billion or million. The part per thousand is a little bit more straightforward. Now, because this is going to be new, let's work through these concentration questions here. Together in number 6, we're looking at trying to determine the concentration of formaldehyde in parts per million. So we know what we're trying to come up with is a ppm, but what does that really mean? Well, we're trying to come up with a 1 part out of a million. So we have options here. We can go with a milligram for every million grams, kilogram, or liter, or we can go a millionth of a gram per gram. So it doesn't really matter how we report our final answer. It might have more to do with the original values. Now, when you look at the formulas for these, of course, it's not very helpful here because all it lists is a ratio of two masses. So I think in this case, we would need to work more with the units and less with the formula, even so with very low concentration. In the case here, we have mass in kilograms. This is the mass of the air. So here, the 500 liter sample of air with a mass of, the 500 is not as important there. That just happens to be the volume of air. It's a solution of different gases, so its mass is really all that we really need to grab. We can go with, as I mentioned, microgram per gram. We can go with a milligram per kilogram, or we can go with a milligram per liter. So here, let's start out with a mass ratio, because remember, very low concentrations are always weight to weight. Okay, and looking at our units for formaldehyde, which would be our solute, it's mass of solute divided by mass of solution. Let's just make sure we try to put our units in a form that matches the part per million, and that will be an easy way of getting the number of parts per million. So we want milligrams. Okay, we've got milligrams, so we have 3.2 of them. In this case, the number of kilograms, great, we've got kilograms, is 0.59. So we know that our final answer is going to be in milligrams per kilogram, and a milligram per kilogram is a part per million. So we just have to match our units, and in this case 3.2 divided by 0.59 is approximately, to two significant digits, 5.4. So 5.4 milligrams per kilogram, or about 5.4 ppm. In your worksheet here, number 4 is going to involve parts per million as well. So here, we're trying to find a volume. And in this case, our concentration at 4.5 parts per million is elaborated a little bit on. It's 4.5 milligrams for every million milligrams, which is a liter. Okay, so remember, a liter is 1,000 grams, which would be a million milligrams. So here we have 4.5 as our concentration, and we're trying to determine what volume of water would contain 100 milligrams of oxygen. So our solute is oxygen. Well, I think here in this case, the volume that we want would be found by just taking the mass that we're trying to obtain and divide by concentration. And now here, because the part per million can sometimes be related to volume as well as mass because of the density of water, we're kind of borrowing on this relationship here between concentration, mass, and volume for, we could say, the percent weight to volume. And so in this case, the crossover sometimes in very low between weight to weight and weight to volume occurs. So we may want to make use of this relationship here, where if we wanted to solve for volume, it would be mass divided by concentration. And we need to work with, back here, the mass being 100 milligrams. And how many times does 4.5 go into 100? That's how many liters we would need. So 4.5 milligrams for every 1 liter would tell us that there is going to be many liters required. So 100 divided by 4.5 is 22.2. So it would be approximately 22 liters of water required before you get 100 milligrams of dissolved oxygen. So that may not appear to involve really the very low concentration, but it does. The unit there is milligram per liter, and we're working with concentration, mass, and volume in this question. So what I would suggest here to wrap up, you're going to want to finish the questions there that aren't started yet in class. When you get into the molar concentration, you probably have an easy time with those. They're pretty easy to work with because we've been using moles for so much in the course. I would suggest, though, just looking at this last assigned work page, that if you're wanting more practice with the part per million and the percent concentration, so concentrations in everyday life, questions can be found on 288 and 290 to 291. Questions just dealing with mass, volume, or concentration. You've got your student worksheet and then additional practice questions if you need to strengthen your understanding. And then there's some wrap-up questions at the end of the section. You may not need to do much of the questions outside of the worksheet, but if you're looking for additional questions, that's where you'll find them. Okay, so we've now introduced concentration. We can, from this point, move on to looking at how do we prepare solutions of a given concentration, and that'll be the next section we'll look at is the standard solution and dilution. Take care.